In this video, we're going to take a look at how to calculate the pH given the Ka of an acid. Remember that this is different from calculating the pH of a strong acid. If you had a strong acid, it would be pretty straightforward. You could just take your H3. So let's just pretend we had a strong acid instead. So let's say in this question, I had HCl. And you don't have to copy all this down, but just pay attention to what's happening. We have HCl plus H2O, liquid, and then that's going to go one-way arrow because it's a strong acid over here to make some Cl minus, aqueous, plus some H3O plus. And so when you put this HCl in the solution, essentially 100% of it is going to ionize. So if you had 0.64 molar here, since it's a 1-to-1 ratio here, you would have 0.64 molar of the H3O plus, and then you could simply do pH is equal to the negative log of 0.64, and you would get your pH value. So you'd get negative log of 0.64. And you would get a pH of 0.193, and then, well, 2 sig figs, so 0.19. So a very, very, very low pH, quite acidic in that situation. Essentially all of our HCl became H3O plus here, 100%. So you could make that direct relationship there, 1-to-1 ratio, since it's 100% ionization. That won't be the case for weak acids. So this only works for strong acids. For weak acids, we have to take into consideration the fact that it's not 100% ionization. So if I have 0.64 molar of the weak acid, it doesn't mean that I'm going to have 0.64 molar of H3O plus. I'll have a lot less than that because the ionization is not 100%. So we have to create an ice table and figure out how much of the acid actually ionized, and then we can use that concentration of H3O plus to figure out the pH. So we're still going to use concentration of H3O plus to figure out pH. It's just the way we find it's a bit different. We have to use an ice table and use some equilibrium concepts rather than just do a 1-to-1 ratio or whatever it is because it's not a strong acid. So let's start off by making our equation for the weak acid HClOAQ. We're going to make it react with water, which is liquid. We're going to put our double arrow because it's a weak acid. We're going to get ClO minus because we gave away an H. And we're going to get H3O plus because that one received an H. And so our goal is to find the concentration of H3O plus, but again, we need to make an ice table because it's not 100% ionization. So let's make our ice table and write out some information that we might know. We know the initial concentration of the solution, which is 0.64 mole per liter. We don't care about water, and we know at the beginning it must have been 0 and 0 because you have to throw your acid in and then it will ionize eventually. Our change will be plus x over here and plus x based on the molar coefficients. You know that already. So our result will be x and x. Here we'll have minus x, and we don't know what that is because we don't know how much ionizes, but the end will be 0.64 minus x. So our goal is to find this x value, so that way we can do the negative log of that x value, which is the H3O plus. So we need to solve for x. How do we do that? Well, we need an expression to do that. So let's create a Ka expression because we have a weak acid here. So we're going to have a Ka. So Ka is equal to the concentration of the H3O plus times the concentration of the ClO minus over the concentration of HClO. And if we were to plug all these values in, we get x times x over 0.64 minus x, which is x squared over 0.64 minus x. So now we can just plug in all our information. We have the Ka given to us. If we didn't, we would go to our table to figure it out. So 2.9 times 10 to the power of negative 8. And that shouldn't really be mole per liter because you don't have to report units for equilibrium constants. So times 10 to the negative 8 is equal to x squared over 0.64 minus x. So our goal is to solve for x. If we continue this way, we'll probably have to use a quadratic formula. I don't want to do that, so I'm going to check if I can do the 100 rule. So that's the initial concentration, so 0.64 over the Ka, which is over here. And if you put that in your calculator, you'll see that it's much greater than 100. Therefore, we can simplify. And so that means we can remove that minus x part from the denominator. So we'll get 2.9 times 10 to the power of negative 8 is equal to x squared over 0.64. And now we can simplify. It's nice and easy. So x squared is going to be 0.64 times 2.9 times 10 to the power of negative 8. And therefore, so I'm just going to continue this up here. X is going to be equal to square root of that value, square root of 0.64 times 2.9 times 10 to the power of negative 8. So we'll do 2.9 times 10 to the power of negative 8 times 0.64. Let's square root that, and we get this 0.000136235 molar, because now we have a concentration. That X value is simply the concentration of H3O plus. It's also the concentration of ClO minus, but we don't really care about that because we want to find the pH. So our last step is, let's now take the pH is equal to the negative log of H3O plus, which is the negative log of the 0.000136235. It was basically this value here, which is equal to, so negative log, I keep everything in my calculator, so I'm not rounding too early, 3.86571114, which is approximately, so pH is approximately to, how many sig figs do we have? 2 sig figs, 3.9. So notice this pH was higher than the one that we did if we were doing HCl of the same concentration. So when we had the same concentration, given us similar concentrations, the strong acid will have the lower pH, the HCl, because all of it became H3O plus. But for the weak acid of the same concentration, we have a bit of a higher pH. It's not as acidic because not all of it becomes H3O plus, and that's what the pH is based off of. So it's not as acidic given similar concentrations. A weak acid could definitely have a lower pH than a strong acid if it's more concentrated. It will definitely take a lot more to make up for it. So you'll have to have more concentrated HClO compared to HCl to get a lower pH. So concentration really will determine your pH, but you need less concentrated acid if it's strong to have a lower pH compared to if it's weak to have a lower pH. So remember, the HCl AQ of the same concentration had a lower pH. It was a pH of 0.19. And that's because all of this 100% became H3O plus. Whereas here, it was only a small percentage that became H3O plus. And so this is how you would calculate the pH of a weak acid given the Ka. It's different than calculating the pH of a strong acid. You don't need a Ka because all of it becomes the H3O plus. In the next video, we're going to take a look at how to calculate the Kb for a weak base. And then after that, we'll take a look at how to calculate the pH for a weak base.